So let's return then to what we had for our global equations, right? So we return to C transpose K bar D bar equals C transpose F bar internal plus C transpose Fj. All right. On the previous slide, we looked at how we use our mesh connectivity information to construct these global matrices K bar and global vectors F bar internal and Fj. The next thing we do here is account for Dirichlet boundary conditions. Okay. Now, suppose that global degrees of freedom right A bar B bar and so on, right, belong to a set that I'm going to call A sub D, right? Or maybe I should be calling this A bar sub D, okay, which is the set of global degrees of freedom on which we have Dirichlet boundary conditions specified, okay. This is the set of global degrees of freedom on which Dirichlet boundary conditions are specified. Okay. Well, we know that if A is the local degree of freedom in some element, if A is the local degree of freedom in element, say EI, okay, corresponding to global degree of freedom, say A bar belonging to the set, right, the set of Dirichlet degrees of freedom globally, right. If this is the case, then we know that in that element WH sub EI, right, is constructed as a sum B equals 1 to number of nodes in the element, B not equal to A, NB CBE, right. This we know very well, right. Okay, which essentially corresponds to the fact that when we look at the, right, we see that this implies that now when we look at the C vector, C transpose, right, it will have you know, C whatever, C D bar, C E bar, right, corresponding to various global degrees of freedom, except that what will happen is that there will not be, you know, it will just go on like this, right? F bar and so on. But what will be missing here is A bar degree of freedom will be missing. Okay, all right, and this will hold for all degrees of freedom that have the Dirichlet boundary conditions specified on them, right? So if this is so, we know that now the dimension of C transpose is going to be somewhat reduced, right? So now if the measure of set A bar D, right, which in this case is just the number of degrees of freedom belonging to this set, right? If measure of A bar D, which is the number of degrees of freedom belonging to A bar D, right? If this is equal to ND, okay, what we know is that we can say something about the size of C transpose, right? What we are seeing then is C transpose is a row vector of dimensions the following, right? Number of spatial dimensions times total number of nodes in the problem, right, minus n sub d, right? This is the dimensionality of the row vector C transpose, okay? But our vector D, our global vector D, sorry, or our global vector D bar, okay, as we've written it in our global matrix vector equations, has all number of spatial dimensions n sub sd times number of nodes. Okay, of course, number of spatial dimensions, because we're developing a problem in 3 dimensions, is 3. Okay, all right. But then we also observe that D bar consists of entries which are the form D1, D2 and so on, okay? But now let me see. We said A bar and B bar belong to the set of global degrees of freedom on which the Dirichlet boundary conditions have been specified, right? So when we come to dA bar, dB bar, right, going all the way down to D NSD times number of nodes, right? What do we know about dA bar and dB bar? We know them, right? These are known. Okay? So, what this also tells us is that our global matrix K bar has dimensions, number of spatial dimensions times number of nodes in the problem minus the script ND, right, those many rows, okay, times the full number of columns. Okay, so K bar is not a square matrix, right? It's a rectangular matrix. Okay, right? So the situation that we have now is in C transpose K bar D bar equals C transpose F bar internal plus C transpose F J, right? Well, some of the degrees of freedom in D bar are already known, right? And those are the ones that are known. Okay? So what we do is we simply move those, the columns from the K bar matrix, right, that correspond to the known degrees of freedom from the D bar matrix, from the D bar array over to the right hand side. Okay, so what we will do now is the following, right? So what we say is that C transpose times a reduced matrix K times a reduced vector D, okay, equals C transpose F bar internal plus F j minus C transpose times K bar. Now for K bar you will have the A column, the A bar column, right, times the dA bar degree of freedom. The dA bar degree of freedom here is just a scalar, right? Likewise, you will also have C transpose times the K bar B bar column times the scalar degree of freedom dB bar. Okay, let me specify that this as well as that are A bar and B bar columns of the full K bar matrix. Okay, likewise the D matrix now is obtained by removing A bar and B bar degrees of freedom, right, and any others, right, degrees of freedom from D bar. Okay, right. Now this is done for all A bar, B bar, belonging to our set A bar D. Okay. All right, so what are we left with then? We are left with a system, right, in which we have a system of the form C transpose K D, right, where the dimensions of K now is NSD times number of nodes minus the size of this set of Dirichlet degrees of freedom, essentially square. Okay, I'm sort of abusing notation a little here. And of course, C transpose and D are vectors also of the size NSD times number of nodes minus ND, right? Okay, this minus F bar internal minus Fj minus K bar, the A bar column of the original full K bar matrix multiplying dA bar minus the B bar column of the original rectangular matrix K bar multiplying the dB bar degree of freedom. Okay. All right, and this entire vector now, right, also is of dimension NSD times number of nodes minus ND, right? It has to be, right? And indeed, the way we've set up things, it is that, right? It does have that dimension. Okay, so all of this has to be equal to 0, all right? Right, so then this has to be equal to 0 and this has to be equal to 0 for all C. Sorry. Right, let me write it down here. This has to hold for all C belonging to R with that dimension, right? Number of spatial dimensions times number of nodes minus ND. Okay, and you remember where that requirement comes from. Right, it comes from the requirement that C degrees of freedom are the ones that interpolate our weighting function. Okay, since this must hold for all C transpose in that space, the only way this can work out is if we have KD equals everything on the right hand side, everything that makes up that vector, right? F bar internal minus Fj minus K bar A bar d A bar minus K bar B bar d B bar. Okay, and now of course we're going to call all of this our final forcing vector. Okay, so we've arrived at the same matrix vector form of our final finite element equations, right? KD equals F for linear problems. Okay, so this is our final matrix vector equation. All right, we are going to stop this segment here.